Pre-calculus 2.7 day 1 notes. And actually, we're just doing 1 day this year on them, so it is just our notes for 2.7 for the 2021 year. And in other years, it will be just day 1, and there will be a day 2. So anyways, so on this, you're going to be solve polynomial inequalities. And so this is different than with equations, where you're just looking for zeros and specific values. Here you're going to have a range of x values as solutions. And we aren't going to get into solving the rational inequalities. That's something that you might want to go in and look at on your own. We're just going to work on solving polynomial inequalities, not rational ones. And so then finding test intervals for a polynomial is much the same as what we've been doing. Find all the real zeros of the polynomial and arrange the zeros in increasing order from least to greatest. So that's similar to what we've done in the past for graphing. And then these zeros are the key numbers of the polynomial. And then use those key numbers to get test intervals and choose one representative x value in each test interval. And we're going to determine if the polynomial is positive or negative. You've experienced this before, and this is going to help us solve the inequality. So in this first example, I basically want to start by figuring out where is this equal to 0, which if I factor and I have an x minus 6 and an x plus 1, the zeros are x equals 6 or negative 1. Now, I'm actually solving where is x minus 6, x plus 1 less than 0. And I'm going to to put them in the right order, I'm going to put them on a number line. And those are zeros of this polynomial. And that is going to give me intervals to test, just as we've done before, from negative infinity to negative 1, negative 1 to 6, and 6 to infinity. And you need this chart. You need to show your test numbers, which negative 2 would work here, 0 would work on that, and 7 will work here. And then you need to show that you are putting them into your factored form and determining the sign. So we don't need the actual value, but we just need to know the sign of each quantity. So with negative 2, the first quantity is negative, the second quantity is negative, and that product is positive. With 0, the first quantity is negative, the second is positive, so overall the polynomial is negative. And with 7, they are both positive, and so that last interval, the polynomial is positive, being above the x-axis. So we have positive, negative, and positive. And my key these are my key numbers. And if I think about this, this is a polynomial. It's a positive 1x squared. So if I was thinking just about a very rough sketch, we have at negative 1 and at 6, we have intercepts, and halfway in there, 6 and a negative 1 is 5. So at about 2.5, we have an asymptote. And somewhere on there's a vertex, but it's opening up. So I've got this polynomial that would be graphed something like this. It's just an idea, just to kind of bring this home. And we are looking for values of x that I can put into, here that will produce values that are negative, less than 0. Well, here at negative 1/2, the output's negative. Here at 1, the output's negative. Here at 5.2, the output's negative. All of these x values in here are values that when I put them into that polynomial, I am getting negative values. So all of those x, it's not just 1 or 2, it's an infinite number of values that are going to make this polynomial negative. And I don't want where it's 0 because this is just less than 0. There's no equality sign. So -1 would make it 0, 6 would make it 0. So I can't include those, but I want everything in between. Basically, I want -1 is less than x is less than 6 is my solution set. But you will write it in, if asked for in interval notation, my solution are from -1 to 6. All those x values make this true. So you still need to find your key numbers, show that you factor it, get your zeros. You need to show how you get your chart with your intervals, your test numbers, and you need to have all this work in here to verify how you know it is positive or negative. Example 2. Here we have 3x squared minus 11x squared equal to 0. You must compare to 0. You need to get everything on one side compared to 0, so that sometimes people don't do that, and then the whole problem is just wrong. You need to move that 4 over and compare to 0. And then remember, we are going to actually solve to find the actual zeros of this, and hoping that this will factor. And so I've got a 3x and an x. I need a minus 11. So what if I did a minus 4 and a plus 1 here? That'll be a minus 12. Plus 1 is a minus 11. So those are the factors. So my key numbers are going to be -1/3 and 4. What makes those 0? Now, but remember, I'm actually solving 3x plus 1, x minus 4 being greater than or equal to 0. And on my number line, I have my -1/3 and I have my 4. Those are both zeros. And so then I've got my intervals I need to set up. So my intervals are -∞ to -1/3, -1/3 to 4, and 4 to infinity. And I need my test numbers. And to the left, -1/3, I would use a -1. Between -1/3 and 4, I would use 0, and then 5. And then we plug them into that factored form and show the signs on each of those quantities using our test number to determine the overall sign of the quadratic. And yes, you need all of this work. So putting in -1 into the first quantity is negative, and second is negative, comes out positive. Putting in 0, I get a positive and a negative, which is negative. And putting in 5, I get a positive and a positive, which overall is positive. And so if I'm thinking about the graph on this, if I'm at -1, then 1, 2, 3, and at 4. So at -1/3 and at 4, and this is a parabola with a positive leading coefficient. 3 is positive, so it would be a parabola opening up, and then somewhere halfway between 3 and 4, we could actually figure it out, but somewhere halfway in between there is going to be my vertex, and we won't worry about actually finding the value, but just the idea of the sketch of this. And now I want where x values where this is 0 or greater than 0. So if I put in a -2, that's going to be way up here, and I have a positive output. If I put -1, it has a positive output. If I put a -1/2, it has a positive output. Those are all x values that are making this positive. So all of these x values to the left of -1/3, if I put them into this inequality, I'm going to get y values that are positive, which means these x values are making that inequality true. Likewise, if I go to the right of 4 and I have a 5, the output's positive. If I put 4.5 in, the output's positive. If I put 6 in, the output's going to be positive. Any number to the right of 4 is going to have a y value that's positive, and at 4, it is the value of the function is 0, and this contains equality, so I actually want the zeros. So I've got a split here. This these two intervals make that quadratic positive, but I also want where it equals 0, so my solution set are going to be x less than or equal to -1/3 or x greater than or equal to 4, because 4 and -1/3 make it 0. We want where it's 0, so those are included. So using interval notation, that is -infinity to -1/3 inclusive, union inclusive 4 to positive infinity. And so that would be my solution set. So in this next one, you see 4 terms. It's not compared to 0, so the very first thing you want to do is compare it to 0. And then you need to factor it. And it might be a rational root theorem to figure out the factors. In this case, there's 4 terms, so I can look for factor by grouping and see if that works. And so in the first 2 terms, I can take out an x squared, and I'm left with a 3x minus 4. In the second, the last pair of terms, I can take out a -4. 12 and 16 are both divisible by -4. And if I do that, I get a 3x minus 4. So, oh, that was nice. It factored by grouping. And notice that 3x minus 4 and 3x minus 4 match. So it is factoring by grouping. So I'm left with x squared minus 4 and 3x minus 4 greater than 0. But that first quantity of x squared minus 4, it's of degree 2. There are two solutions, including complex solutions. And so on that one, it still factors. It's a difference of squares. So you need to keep on going down to get all the values of x that make this 0. I have an x plus 2 and an x minus 2. And so my key numbers are going to be all the values that would make this 0, which would be -2, +2, and then +4/3. And if I would put those on a number line, mostly just to make sure I get those in increasing order, I have a -2. 4/3 is 1 1/3, so that's going to come before 2. And each one of those happens to make this 0. So if there's 3 key numbers, you will have 4 intervals. So on my intervals, I have -infinity to -2, -2 to 4/3, and then 4/3 to 2, and then 2 to infinity. In here, I would use a -3 and zeros between -2 and 4/3. 4/3 is 1 1/3, so maybe 1.8 or 1.5. And to the right of 2, I would use 3. And then we're going to plug these into the factored form. So we're going to test each of these quantities to determine if each quantity is positive or negative using the test number. You need to show this work. If I put -3, the first quantity is negative, second's negative, and -9 minus 4 is negative. If I put in 0, I get a positive, a negative, and a negative. If I put in 1.8, I have a positive. 1.8 minus 2 is still negative. And 3 times 1.8 is going to be 5.4. And that's going to end up making that positive. And if I put in 3, I have a positive, and a positive. So as I'm multiplying those, I'll end up negative, and then positive. And so what that graphically means is at -2, I have a 0. At 1 1/3, I have a 0. And at 2, I have a 0. And it's a polynomial, so it's a smooth continuous curve. We are alternating from negative to positive in this case. There is no bounces because none of these factors had a power other than to the first. And so it's coming up from below and crossing at some point, crossing back and being negative between negative 4/3 and 2 and going back up. And then the y-intercept, I mean, if I put 0 into this equation, the y-intercept would be 16. So however it's working here, and that might not, it's not a perfect sketch exactly, but it's close enough to kind of help. And so I want to solve this inequality right here. I want all the x values, oops, now you got on the wrong line. I want all the x values that make this greater than 0. So what kind of x values are making this greater than 0? Well, at -1, the output's positive. So there's one. At -1/2, the output's positive. So there's another solution. At 1, the output is positive. So there's another. All of these x values between the -2 and the 4/3 are making the result positive. So those are solutions. And then to the right of 2, if I put in 3, the output's positive. And any number beyond 3, 2.5, the output's positive. All those x values produce positive y values, meaning that, the graph being above the x-axis, those are values where this polynomial is going to be positive. And so we're looking at those two intervals. In this case, there is no equality I don't want where it's 0. So my solutions are going to be between -2 and 4, oops, that needs to be at 3. -2 and 4/3. And when you write inequalities, I always put the smallest on the left, use less than in both, and then the larger on the right. But that's not the only, or x could be greater than 2. All those x values, if I plug them into that polynomial, put out y values that are positive. So those are my solutions. So using interval notation, I'm going to have -2 to 4/3 union 2 to infinity. And so those are my solutions. You need this work to justify your answers. You need complete sum. All of these greater than zeros as you work down need to be shown as you're working through that. Don't drop that part off. Be a stickler for those details as you work through your homework. All right, then we have some unusual situations, all reals or no solution. So we have this x² plus 6x plus 12. And if I try to start factoring this, I can't figure things that multiply to be 12 to add up to be 6. It's 1 and 12, 2 and 6, 3 and 4. None of them are adding up to 6. None of the ones. So then that makes me kind of wonder, does this factor? And if I look at the discriminant, which is your b² minus 4ac, what goes underneath the radical? 36 minus 4 times 1 times 12. I get 36 minus 48, which is negative. That means I have two complex solutions, two imaginary. And when that happens, that means this does not ever touch the x-axis. Doesn't ever touch the x-axis. So if I think of solving this equals 0, and negative b plus or minus the square root of 36 minus 4 times 1 times 12 all over 2a. I have a -6 plus or minus that square root of 36 minus 48 is a -12, which is a -6 plus or minus 12 is 4 times 3, which is 2 root 3, but it's imaginary, so 2i root 3 all over 2. They both divide by 2, so I have two imaginary. There are no real solutions. So you need to have work to verify how you know that there are no real solutions. And if I use that x is a negative b over 2a to get the vertex of this, negative 6 over 2 is a negative 3. And if I plug that in to get the y value, I get a 3. So the vertex is negative 3, 3. So the graph of this here's the vertex, but it's a parabola opening up, and the y-intercept is up at 12, so it's going to be going up like that. So this is for all x. So for all x values, y is positive for all x values, no matter what you put in. And since I'm solving for where is this greater than 0, my answer, my solution set, is negative infinity to infinity. It is all reals. You need to come out and state that. Any x value you put in there, it's going to come out positive. Now, in contrast, just kind of an extension of this, would be, what if I took that same quantity and I asked, where is it less than 0? Well, I just went through this whole thing. We graphed it. We talked about their imaginary solutions. And for every x value you put in there, you get a positive y value. And I want to know, for what x values will this be negative? And there are none. This would have no solution. There are no values